Thanks, Daryl, and it's great to be here. For those who don't know, Codenomicon has been here at Plugfest. We've been improving our interoperability with various storage protocols, including SMP2, SMP3, and CIFS. But then a lot of people came to talk to me during this week, coming to ask about how Codenomicon found the HeartBleed and just talk about things generally. So then we were really busy doing our testing, so then it just evolved to the point that there was an opportunity to present here. So we came up with Daryl that let's have a small little session here, and really instead of I'm not really gonna talk actually about what HeartBleed is, kind of what gets lost, what's the remediation, all that. I think that has been really well covered in the press already, and there's excellent information if you go to heartbleed.com or any other sites. I think that's been covered, but what I thought of showing, which I think is something most people haven't seen, is how the actual private key extraction works. And kind of walk through that part and show some of the theory behind it. Since I think that was not only one of the kind of parts that was really misunderstood in the beginning, and where a lot of debate was, but it's let's look into it. And few words about Codenomicon. I don't know if you've heard about us before, but nowadays I guess we are the company that is known about the HeartBleed. Before we were also known about, due to the other vulnerabilities we had found, including the big SNMP vulnerabilities through Protos Research Project back in the day. And then generally at the Plugfest like this, we are known as the people who come and crash your software while we try to interoperate. Since that's really what we do. But really what we do as a company, we are makers of software that as a developer helps you to build better software. And then our buyer side customers, they use our software to then take the software you deliver to them and make sure that when they deploy it, it's robust, it's secure, it's reliable. And that's really what we do. We make software and we come to the Plugfest and other places to make sure that we work as well as we can, since in order to do effective testing, especially protocol testing, you have to interoperate, you have to be able to do go to the right state and then send in the punch in to knock the software down. We have presence in North America, Asia, and Europe. Most of our R&D is in Finland, where I come from, and our CEO sits in Saratoga, California, where I'm based nowadays. So what we do, it said on the previous slide, we are focused on unknown vulnerability management. In layman terms, I would say fuzz testing or fuzzing. And this is a great definition. I'll read it out. Fuzzing is the process of sending intentionally invalid data to a product in the hopes of triggering an error condition or fault. These error conditions can lead to exploitable vulnerabilities. And I think this is really important to keep in mind. And I get back to this a little bit in regard to the methodology, how we found HeartBleed. But fuzz testing is what we do and what our software does. And I've sometimes actually compared it a little bit to my English language. It's English with a little twists here and there. It has some imperfections. I hope no one goes to denial of service because of what I say. Just rather ask, hey, can you repeat that? So, long story short, let's get to the HeartBleed. And I would say it's the most significant single vulnerability in software since maybe the beginning of software. And it is in the RFC 6520, which is the HeartBleed extension to the TLS SSL protocol. And the HeartBleed or HeartBleed bug, it is in the OpenSSL's implementation of that feature. And what it allows you to obtain is the private keys of the server, which is what I'm going to talk about that today. And then in addition of that, some other data that happens to be in the active memory of the process that has the vulnerable OpenSSL. And that can be usernames, passwords, session tokens, cookies, whatever happens to be there. But by far, if you ask me, it was really the key ability to steal the keys that set this bug apart. And kind of like to set the stage, I don't know, how familiar are you with the TLS SSL handshake, how it works, how the what client sends to the server, and what the server replies in order to get the shields up, that is the cryptography in place. So Just as a quick refresher, if you look here, this is how it really goes when a client, let's say web browser or LDAP client, when it connects to the service that's protected by TLS SSL, it starts with client hello, where it sends that, hey, these are the cipher suites I'd like to use. And then the server replies with, hey, okay, here's my hello, and here's the cipher suite I choose, and a few other things. And here's, by the way, my certificate and my public with my public key. That's important for later. And then from there, they go to exchange the keys and keying material. And then finally, they say that, hey, we're both happy, shields up, let's start debating encrypted. And here, by the way, server can request that, hey, by the way, I want to use client certificate for validation that you are who I think you are. So it happens here. And as I will go back later in the presentation, HeartBleed can be sent inside the encrypted tunnel, or it can be already also sent during the handshake period, before the client certificate request is actually handled. So if you are using client certificate validation, it won't protect you. And I'll get back to that later. So how does the HeartBleed message actually look? And this is from the spec. And I'll show that you also in Wireshark to see so that you can see how it looks in the wire. But really what's there is underneath this, there's a TLS SSL record, inside which there is a HeartBleed message with a request or reply as a type, and inside that there is a payload length and then padding. And the payload length really defines how much data I'm sending to the other end, which I'm supposed to get echoed back. And the idea is that I send hello, and it sends hello back, and I indicate that hello is likely 5 bytes that I'm getting back. Now, the vulnerability is that I can send the hello, or in fact, I can send 0 bytes, and I can still say that, hey, my payload is 64 kilos. And server is happy to read whatever memory it happens to have and send it back to me. Now, what makes this interesting is that OpenSSL used its own memory allocation routine, which amplified the problem that under most normal circumstances, if you try to allocate that much memory, you would end up seg faulting or access violating, doing something. But because of how their custom-built memory allocator worked, it just keeps chucking memory that is in the same space where other processes have been allocating memory, and you get their content. So it's kind of funny. And XKCD, I don't know if you've seen this. I think it offers great explanation for the rather technical thing that I explained. I recommend you to go take a look if you haven't. But a couple of words, I guess, why it's so bad. Again, the private key leakage. If someone was recording traffic, great, you could get the keys, read it. And then I think a couple of other things. It's platform independent. Like with most other exploits bugs, it's a Windows bug, it's an Android bug, it's a Linux bug. But this was really like any platform, any software that chose to use vulnerable OpenSSL was theoretically speaking vulnerable. And it didn't really require exploit. I mean, exploits can be written for a variety of things, but I would argue that oftentimes, especially nowadays with all the sandboxing technologies and others, creating an exploit, especially one that's like easy to launch. Some people talk about militarized exploits. It's not easy, and they get easily ruined. HeartBleed didn't really require exploit. All that was required was to send that packet and get the memory back. That's really all you needed. There was no exploit development. Like some people I talked, they said that, well, once I understood it, in a matter of like 10 minutes, I had I wouldn't say exploit, but I could actually start leaking the memory. Few lines of Python. And then, of course, and this really, I think, goes to, if we would like to talk about like what to do, but it wasn't just like web bug. It's also like everything else that used OpenSSL, vulnerable OpenSSL, for TLS SSL traffic. And that includes things like LDAP-S IMAP-S, SMTP-S, XMPP, pretty much anything that you can think of and can't think of running over the TLS SSL. So then a couple of misconceptions we have run. One is that if you use client certificate, it will protect you. So I'll get back to that. And then the other, especially initially, people were saying, a lot of people were saying that, hey, 16 kilos is all you can leak. And I show you where that came from and why it's not actually true. And then a lot of debate has gone into like how we found it, how others found it. And well, we found it. I can't speak for the others. We found it through fuzz testing. That's why I was spending a few moments on it. And in particular, we found it with the safeguard feature set of our fuzz testing engine. And those who are familiar with the fuzzing, the idea with the fuzzing is that you send these unexpected inputs in order to typically find failure modes such as crashes, busy loops, some sort of a resource allocation where you consume file handles, something else that which eventually like just knocks down your system. Now, the safeguard feature set that we have been developing, which got released a little while ago, it looks for things beyond these traditional failure modes. It fuzzes your target, and it looks if, hey, like, did I get back what suspiciously looks like contents of the memory? Check. That's how we found HeartBleed. But in addition of that, we look for things such as authentication bypass, amplification. You may have heard about the NTP having issues lately with sending a really small packet and that getting replied with a really big packet, which you can use then as a reflected attack against other hosts. So we look into that kind of thing and alert on things such as weak cryptography. But I think if we look at the client request thing, this is a this is from the RFC, and in the RFC 6520 it says a heartbeat request message can arrive almost at any time during the lifetime of a connection, and then it goes on to say, however, heartbeat message should not be sent during handshake. But OpenSSL, who by the way is written, I believe, by the same people who wrote the RFC, it chooses still to accept it during the handshake before the shields are up. So yeah, you can and that's by the way, when I actually demonstrate how to extract the key, just for the ease of following, I will use the pre-session or the HeartBleed that's sent before the shields are up, since it's then so easy to see what happens signaling wise. But I think since there are some people working with the specs here, I think this is a great example how open-ended specification, then when someone implemented it, then they unknowingly, I would argue, ended up doing a feature which then jeopardized more hosts than would necessarily have been jeopardized if they had been actually following the recommendations of the specification. So, I mean, they weren't wrong according to specification, they just chose to ignore the recommendation it gave, I would say. So I think that was an interesting finding, and it and all kind of sidetrack. Now then, another thing was this 16 kilo limit, and elsewhere in the spec, and I admit this is if you haven't worked with a TLS SSL, it's a record-based protocol where the spec says total length of a heartbeat message must not exceed 2 times or 2 to the power of 14, which is 16 kilos. So yes, that's the actual heartbeat message. But nothing. But if you request for 64 kilos, it just means that a single heartbeat response is no more than 16 kilos, so you'll get 4 of them, or however the server chooses to fragment the packet into the different record layers. So that was kind of coming from the spec, easy misunderstanding, I think. And it actually, when you are milking the memory of the server, it does make a difference whether you get 16 or 64, since you get much more interesting stuff under the 64 kilos. So I think that was one of the more interesting things there. But finally, approaching our thing, so let's look into how the actual key extraction works. So first, what I have here is I have a virtual machine here, which is, let's see, which is running on the, there, 172.16.56.104. And I have a light HTTPD running here. And if I look into it, it's I have the vulnerable, little old OpenSSL 101C here, which is vulnerable to HeartBleed. And then, just to make sure that the web server actually uses it, just checking that I'm linking to the right vulnerable libraries. But that's it. And if I look there, I can go here. And that's the website I'm accessing to. Try to make it a little more storage specific, but I imagine that with quite a few of your storage solutions, you do have a management interface, which is HTML based, and where you can actually where you do use OpenSSL. And I think, by the way, storage industry, and I'd like to hear your opinions. Like, you were lucky that I'm not aware of TLS SSL specifically being used as part of any storage protocols that I can think of. Oh, it does?
I think.
Okay. Jeremy?
Actually, very, very old versions of Samba had a custom extension where you could tunnel SMB1 inside SSL. So
is it still there?
Who knows how many old versions of Samba are out there still running?
Sweet.
So it's possible.
Sweet. And that's actually scenario-wise not very far from... Oh, sorry. So the question that I asked was that are you aware of any storage protocols that run TLS SSL inside? And to my surprise, what I heard was that Samba org has some old versions, I believe, very old, that actually allow tunneling TLS SSL or securing Samba connection by negotiating TLS SSL inside the SMB2 or SMB1 CIFs, I would imagine, LANman, something like that. Yeah, something like that. But so that's going to be one of the closest ones that I've heard. So again, I think storage industry by far, instead of some management interfaces, others, I think we got lucky in that regard. But anyway, so here's the website I'm going to attack, and then, well, I'll use Defensix to run it once. I think I have Wireshark here ready, so let's record it. So what Defensix does, it's just I've selected a couple of test cases here. If I look here, it's you can see how. No, let's go here. I think this will be it. All right. Well, let's see. Oh, wrong test case. My bad. There we go. So there you can see a heartbeat request with payload length set to the 65534, and that's what I'm going to send. And let's see how it looks in the wire. So play that, and going back to wire, you by the way notice I was mentioning about the safeguard. I'm getting the warnings there that hey, like something odd is happening. You have to go back and check. But that said, if you look at what happened in the wire, you can first see here a valid TLS SSL session. There's a client hello going in. Server replies with its server hello, server certificate. And then we exchange the client server key exchange, change cipher specification, and then basically get the shields up, and there's few encrypted messages. And there's, by the way, the encrypted heartbeat message. You can only see the heartbeat record type and TLS SSL version, and everything else is encrypted. Which, by the way, if I were in the business of stealing information, that's awesome, since like only thing anyone can really see is that, okay, a lot of heartbeat requests with quite a big payload is going, but you can't even tell if someone actually like requested. I mean, you could do heuristics that it was a small one and followed by the big one, so it doesn't look right, but it's just like perfect covered channel in that regard. But you can see our encrypted heartbeat request going in there, and then it's followed by, well, very big fragmented, very big few TCP frames that then make up the actual payload that is, sorry, yeah, there we go. Where is it? There it is. I was looking at the wrong place. So here's the actual heartbeat that has the anomaly in, and then it's followed there by the contents of the memory from the server. And that's how it looks in a wire when you see it. Small heartbeat going in and big heartbeat coming out. Now, going back here, so I don't go into this, but then in order to actually understand how the key leakage works, let's take it back. I'm sure most of you, I'm sure all of us have seen this when you took your computer sciences classes. I know that when I did, I saw it and I tried to forget about it as quickly as I could. And the only reason I had to really go back to it is that we happened to stumble on this and we had to figure out how to get the key out. But when you think of key extraction, what you are trying to get is the RSA private key. So first you have to, this is how the RSA private key is specified nowadays in RFC 3447, and this is how it looks. It's an ASN1 structure, or can be other things. But what it has are, there's a few components. There's a version, there's a modulus, public exponent, private exponent, prime 1 and 2, and then some other stuff. Now, the really important stuff are the primes 1 and 2, and then for what we need, the modulus. Those really, and prime 1 and 2 are the primes P and Q, which are the kings of the kingdom. Those are the things you need. And if you have those, you can get everything else. The math is really P times Q equals N, and then everything else comes from there. Check out the RFC 3447. I probably can't remember it, how the rest of the math from top of my head anyways. But there's a really great website, by the way. I'll point you later if you're interested about all the stuff. But to get started, this is how the RSA private key looks. And then when you take that key into the real world and take it to the server, on most Unix servers, this is also, in my opinion, it's probably PKCS 12 what the IIS takes, but it's still a derivative of this or the other way around. But this is how the RSA private key looks under the ASCII armor. And I think, by the way, when you looked at the initial attempt of finding the keys, this is what many people were trying to harvest from the memory dumps, which obviously is you have to think a little faster to understand what's inside, what are you looking for. And if I show you, and that's how it looks then when you look into the ASCII armor to begin with. So I'm here in the directory where I have my keys for my web server, and this is the private key. Sorry, that's the public key. There. So if I look into it, as you can see, it's the ASCII armor. But then if I look inside it, I made a little script for that, But I'm using OpenSSL to just open up the ASCII armor. It shows the commands. I first converted into the PKCS8 format, and then just dumped using ASN1 parse, just parse the components. And if you remember the previous slide, this one is the public module, or this is the modulus N, and then 1, 2, 3. Then these two are the P and Q. So essentially, if you're trying to find the private key from the memory, what you're going after is not the ASCII armor, but these two things here. And once you get there, I think you're almost there. And then, I get back. I get back to that. But assuming you know what the private key is, it's actually pretty easy to determine, and that's what we did, to determine if it leaks. Rather than like spending a whole lot of time with the source code, trying to figure out, like, you just run the attack, or test case in our case. Then like go back to your private keys and let's see if it's in the memory. And I have a pre-recorded session here. So I have a, like you can see, this is like similar, only this is now done before the handshake. So this doesn't have the encryption on it. But like if you look down here, I scroll down and here's the heartbeat request again, followed by the contents of the memory dumped to the wire. So if I want to determine if the keys are in there, I will just go back here. And okay, it's this one. So I want to find this, and then the only thing you have to keep in mind, it's Intel. So what byte order in the Intel uses? Correct. So you probably have to think in reverse. So in order to find it from memory, you take that one, but you just search in reverse. So in order to help myself, I copied it into the notepad here, and then I just took some of the, where is it? Some of the remaining bytes here. I think 5 is usually enough randomness or uniqueness, I guess, to be enough. So I just took those and now you can go to the Wireshark or Redmond or whatever, and I can just hit Control F and copy paste the last 5 bytes of the private key here. And now if I hit find, it takes me to the exact frame where you can see now the key here in little endian byte order. So what I have done now is I have found the prime P here from the memory that the server dumped back. And that kind of alone, I get back to the math a little later, but at this point you know that, hey, damn, I am getting the keys. And then only next step is to like go back to math and think, okay, what are the components, what's the modulus, what's the P and what's the Q? And then if you remember, I mentioned early on that the server does send its public key or server certificate. Nice thing about that is that it does contain the modulus for the server or the N, since that's what it's the server's public key really. So now you know too, and if you remember, modulus is P times Q. So I know now the modulus and I know the P. So only thing left is to determine what's the Q, and that's a really simple math. And I'll get back to that in just one slide. So lastly, I'll show the utilities. And so now we know that it leaks. So now how to make it automatic, how to make it nice and convenient, how to make it easy. So we wrote a little utility which connects to the server, does all fine, asks for it server certificate, extracts the server certificate, pulls the modulus, then issues the heartbeat request, dumps the memory, and then takes the modulus and I lost it. Yeah. So now I lost my thought. But we pull the memory, and since we know the public key of the server, then we just start traversing that. And oh, by the way, that was where I got lost. So then, of course, you have to know the key length. Is it 248 or is it 1024-bit key length? But the great thing is that because you get the server certificate, from there you can tell what's the key length. So that's how you know that when you start dividing things, you can you know how many bytes you have to read. So once you have the modulus, you just start dividing every key length amount of bytes in the memory you get. And then once you get modulus 0, you know that you want one of the primes. and then you just do a little rest of the math, and you determine the Q. And there you go. And to show that, and that's, by the way, been something kind of like a debate around HeartBleed. That how much, what's the key extraction dependent? And I don't have the exact answers. It seems to depend. In my setup, less load is better. When there's almost no load, I get the key like that. With the HeartBleed challenge, it appeared more load was better. With some other setups, it varies. But generally speaking, my experience has been that less load better, but it doesn't seem to generally apply, which is interesting. And I guess it depends a little bit what kind of a server, whether it's an NG-INX, whether it's a light HTTP Apache, something else. It seems to vary a little bit. And then in some embedded systems, by the way, which is why I don't recommend to just test HeartBleed by exploiting it. We've seen that when you actually exploit it, it actually crashes the little embedded systems. So keep that in mind also when trying it. But really, to take the, so let's see. I don't know if you recognize the name Translator. I don't know if you've read this book by Dan Brown. Very bad book, but I gave a funny name. Translator. It was the computer that in his imaginary NSA was able to crack every crypto in the world. So that's why we named it Translator. But I recommend you to, I think they say it somewhere, but get it somewhere, rip it apart, burn it, and don't read it, since it's like insult to the computer sciences. But what I have here is the Translator. Well, actually, it's PI, which is 312 lines of Python. So it's not a very long. It doesn't negotiate TLS SSL really. It's just dumps enough to send the client hello and the anomalous heartbeat request. That's all you really need, and then just reads whatever you get back. And the syntax is, so my server was at and 443, and unless I get a demo effect, I'm bleeding from there. And as soon as I'm bleeding, as I said, with a no load, I get the key almost right away. And it gets the key, and as you can see, it gets the modulus. Then and then from what it gets, it then just works through the math to get everything else, and it constructs conveniently. It saves it to the hostname.zip, so that I now have conveniently the private key pair in right format. If I want to have a fake web server masquerading as that site, I can just throw them there and throw the web server up. So that's how easy it is and how it works. So thank you. It was a nice. And any questions that I can answer?
I actually have a question. I work with an Amazon.
Yeah.
If someone was sniffing in the middle of the wire,
did
they actually? If somebody was sniffing the wire and they already had the keys, so let's say that they sniffed a year's worth of data, but now I have your server keys, could they somehow decrypt that?
Yeah. So that's the idea. Come again? What was,
so let's say I was sniffing you for a year, but I didn't have your keys, but then now I stole the server key of the data, the client data. Would I be able to decrypt that somehow?
Yes. That's the whole that's the scary part, in my opinion, with the HeartBleed, that you can just have years worth of traffic recorded, and you can come back to it at any point once you get the private keys. So that's really where, in my opinion, lies one of the scariest aspects of the whole attack. Thank you. So hey, anyway, if anyone you want to, we're down that way, and if you want to test against us fuzzing-wise, or if you just want to validate the interop with us, since we really want to, as far as our storage tools, we want to make sure we interoperate well. So come talk to us. We'll be here till the end of Friday. So thank you.